Okay, in homework 3 part B for separations, we are really just continuing on from part A. So we're going to be talking about the boil-up ratio and the reflux ratio, as well as the feed composition and some things like that. And we're going to generate what is called a McCabe Thiele diagram using Google Colaboratory with Python. And then we are also going to talk about what happens when the reflux ratio is changed and how that affects the system as a whole. So I'm going to get into some of the derivations, and then after that we will do some code. Okay, so we're going to start with the first part of this problem, derive an expression for the boil-up ratio in terms of the liquid fraction of the feed and the reflux ratio. So as I defined in part A, the reflux ratio is equal to the liquid over the distillate. That is because that is literally what it is there's vapor coming up, going into the condenser. Some of it is taken off as distillate, the D, and some of it is sent back refluxed, and that is the liquid. Also defined the boil-up ratio, which was V sub B, because I didn't want to call it B and confuse it with bottoms, especially because I want to be able to use B for the bottoms and D for the distillate. That is equal to V bar divided by B. And again, we use the bar when we're talking about the stripping section, that lower section. When we are talking about the feed and the Q line, we know that V is equal to 1 minus Q, which we talked about in part A, times the feed plus V bar. And then we can take that a little bit further. We know that the vapor is equal to the liquid plus the distillate, so I'm going to write it just like that. L plus D is equal to 1 minus Q times F plus V bar. And implementing the reflux ratio, we have the distillate times the reflux ratio plus 1 minus 1 minus Q times F is all equal to V bar. We just moved that 1 minus Q to the left and altered our L plus D into the distillate times the reflux ratio plus 1. So since we know that the boil-up ratio is equal to V bar divided by B, we literally just take this equation right here and divide it by divide it by the bottoms. So we have the D times R plus 1 minus 1 minus Q times F, that is V bar, and divide that by B, and we have our boil-up ratio in terms of our feed composition as well as the reflux ratio. So I'm going to circle this in, and this is our VB equation that we derived. So we've done this first part, and now we want to move on to the second part, derive an expression for determining the equilibrium liquid composition if you are given the vapor fraction of the more volatile component in a binary mixture at a fixed relative volatility. So we kind of talked about relative volatility before, but basically we're assuming constant molar overflow, so our liquid and vapor flows are the way that they interact with each other is consistent and ideal. And that is why we are able to do what we're doing today with the McCabe Thiele. And I had to look it up to make sure I was giving this information correctly, but the constant molar overflow idea essentially means that for every mole of vapor condensed, exactly 1 mole of liquid is vaporized, and that is why we get straight operating lines on the diagram that we're going to draw in a little bit. So moving on, I want to kind of go into a few sections. So we have an overall, column material balance. We've written this prior, but I'm just going to do this again. We know that the feed is going to be equal to the distillate plus the bottoms once all is said and done. And the liquid is equal to the vapor plus the bottoms. And that should be bar. We also know that V times n plus 1 is equal to the liquid plus the distillate. I'm just taking everything from part A. In terms of components, we know that the feed times the composition of the feed is going to be equal to the distillate times the liquid composition of the distillate plus the bottoms times that liquid composition of the distillate. And again, when I say composition of the distillate, I'm talking about the more volatile component. And then I'm going to go ahead and talk about relative volatility a little bit more again, even though I did that in a previous video. We denote that as this alpha, and it's equal to K1 over K2, and K is just the ratio of Y over X. So our K1 would be the ratio of Y1 to X1, and our K2 would be the ratio of Y2 to X2. And we're comparing those two to each other. So we're saying that this is going to be constant. Because of what I was saying they're equal to, we end up getting Y1 times X2 divided by Y2 times X1. That is equal to the alpha. And then we can say that is equal to Y1 times we can say that's equal to Y1 times 1 minus X1. 1 minus X1 is X2. We have two components, and they need to add up to 1. We are doing a binary mixture here, as I said earlier. And we want to do a similar thing here, keeping it in terms of component 1. We have X1 times 1 minus Y2. We know that 1 minus Y2 is also, that also needs to be, I meant to say 1 minus Y1. Same thing with the X. We know that 1 minus Y1 is equal to Y2. It's the same the other way around, but we're trying to keep things in terms of the same component. And I'm just going to write this for my own sanity, but obviously all the components, all of the vapor components need to add up to 1 as well. So if we multiply our alpha by the denominator, we get alpha times X1 times 1 minus Y1 all equal to Y1 times 1 minus X1, and we would like to solve. We could solve for either X1 or Y1, but we are deriving an expression for determining the liquid composition given the vapor fraction. So we are being given Y, so we want to solve for X, specifically X1, but solving for X1 would also give us X2. So if we distribute all of these out, we have alpha times X1 times 1 minus alpha X1 Y1 is equal to y1 minus y1 times x1. And we want to get x1 isolated. So first I'm going to divide by y1, and that gets us alpha times x1 over y1 minus alpha times x1 is equal to 1 minus x1. And actually I'm just going to add that x1 to this side. So that is all equal to 1 now. So we have the x1s on the same side of the equation, but we have not isolated it. So this isn't complete yet. If we pull out our x1, we would need to multiply that by alpha over y1 minus alpha plus 1, and that's equal to 1. And so we get that x1 is equal to 1 divided by alpha divided by y1 minus alpha plus 1. And I'm now actually going to multiply by y1 to get it out of this area right there. So we have our final equation that x1 is equal to y1 divided by alpha minus y1 times alpha plus 1. Or sorry, this should be minus 1 right there. So you would get a negative y1 times alpha and a positive y1. How to solve for x1 given y. Right, so we did this. So we basically derived the expression to calculate the equilibrium liquid composition given the vapor fraction of the more volatile component for fixed relative volatility. So that was our equation right there. And we also did that boil-up ratio. And so now I believe it is time to move on to the coding. So we're going to do McCabe Thiele diagrams for constant relative volatility using a total condenser as we've been using. And we are going to demonstrate the code for different relative volatilities as well as different reflux ratios, and we're going to talk about how the reflux ratio affects our column. As I was saying, we're going to do the McCabe Thiele diagrams, changing the relative volatilities and the reflux ratio to see how that changes things. Essentially, with a low relative volatility, you're going to have a more difficult time separating your components because they're going to have similar volatilities to each other. A higher relative volatility means it's going to be easier to separate, so that could mean the difference between needing more stages versus less stages in your column. As always, I have my usual import at the top. And we are going to get started with defining alpha, which is our relative volatility. For now, I will use this first value of 2. So I'm going to set that equal to 2. And first we want to have our equilibrium function. So we have the equilibrium function dependent on y. And we're going to return y divided by y plus alpha times 1 minus y. This 1 minus y would be 1 minus y1, giving us our y2. So this is what we have already talked about before. So I won't go too in depth. And so this is going to give us our equally spaced points. And we want to do a similar thing here with our x values. except they are going to calculate the x value that corresponds to this YEQ value. Now I want to get started with basically our column specs and feed conditions. So setting F to 1, this is our feed flow rate. So that would be in moles per second. I'm just using 1 because that's a pretty simple value, but in reality it would be much, much higher than that. 1 mole is very small. And so this is our mole fraction in the feed of the more volatile component. That wasn't specified, so I'm going to do 0.4 just for now, and set a Q. That also wasn't stated. I'll do 0.8. This is the fraction of the feed that is a liquid. I'm going to set our recovery of the distillate first to 95%, and then I'm going to set XD. This is the purity that we want to have, and I'm going to do 90.8% there, and this is in a mole fraction. And then we also want to set the reflux ratio. 1000 is pretty high, so I'm just going to go with this 2 for now, but I'll also show later on what that 1000 will look like. We've talked about this already, but we have our mass balances. So our D is equal to our RD times the feed flow rate times our ZF divided by XB. Our bottoms, as we know, is equal to the feed minus the distillate. And the composition of the bottoms should be equal to Z times F, or sorry, ZF times F minus the purity of our distillate times the distillate divided by the bottoms. And we had that derived equation for the boil-up ratio earlier, and we're going to just directly put that into here. So that was, we defined that as being equal to the distillate times the reflux ratio plus 1 minus 1 minus Q times the feed all over the bottoms flow rate. Now what we want to do is basically calculate the intersection point of the rectifying and stripping operating lines that we talked about in part A, how to find those. So I'm going to call this X underscore RS for rectifying and stripping. That's going to be equal to XB divided by VB, our boil-up ratio, plus XD divided by R plus 1. And we're dividing that by the boil-up ratio plus 1 divided by the boil-up ratio minus R divided by R plus 1. And I made a little mistake there with the parentheses. Also, sorry if my eyes get like red or watery. We have entered the horrible allergy season in Ohio, so I'm struggling. But to find that R intersection of the rectifying and stripping section in a similar way, R over R plus 1 times the X value that we calculated above plus XD divided by R plus 1. And now we're getting to the McCabe Thiele part of things. First I want to set a maximum number of stages so that if the values I put in just doesn't work at all and it's not converging, it will stop. the simulation. Here is those x values, and I can also, or sorry, that was the y values, and I can get the corresponding x values like that. I can also do our distillate flow, bottoms, etc. The bottoms plus the distillate is equal to our feed, so everything looks okay for now. I'm also going to see if, okay, so that was able to be calculated. I'm sure the y is fine as well. And when we plot, we'll determine if there was an error anywhere, because it will probably look very funky. Our XY steps, we're going to start a list that is just XD and XD. And then our Y equilibrium is, we're starting with XD as well. So we're basically starting our Y composition as being the same as the distillate composition. And we want to set up a for loop, so for I in range n max, which we set up above a few lines. Our x equilibrium is going to be equal to the x equilibrium function at this y equilibrium value that will be consistently calculated. And then we want to append those those x values and those y values. So basically this gets added into our list, which currently at the very start we started with assuming the distillate composition, and then later on, if our x equilibrium is less than the composition in the bottoms, then we break this for loop because we have met the requirement, and you'll kind of see that later on. We also want to define our rectifying the y value if we were to drop to our rectifying line, so where the, I guess, cross section is with that line. So we would do the reflux ratio times our x equilibrium value, divide that by the reflux ratio plus 1, add our distillate composition divided by r plus 1. And we need to do the same thing for the stripping line because, as you'll see later on, we'll kind of have a cross section like this, and we will need to have an intersection not only for the rectifying curve line, but also the stripping line. And I'm saying line instead of curve because these are linear lines due to our constant molar overflow assumption that we talked about. And in in a future video, I'll talk about what we do when we can't assume the constant molar overflow and stuff like that. We can't use the McCabe Thiele plot. But for now, with our assumptions and what we know, we're going to do the McCabe Thiele. So yeah, this, for the strip line cross section, we have the boilup ratio plus 1 times our x equilibrium value, divide that by the boilup ratio, and then subtract the bottoms composition divided by the boilup ratio. And eventually we're going to have to determine if we're going to connect to the rectifying line or the stripping line. And basically, you want to connect to the line that is closest, or the minimum. So I just realized I never showed a photo of the McCabe Thiele, McCabe Thiele diagram, which I definitely should have done earlier so that you have a reference if you've never seen it. But basically, this is for two substances specifically right now. And this is kind of what a graph would look like. So we have our rectifying line up here and our stripping down here. So when I say we need to find the minimum, we're determining would it be better, and this line would extend past here. So we're determining would we want to do a step down to that line, or should we go all the way down to the stripping line? And obviously the stripping line is at a minimum. So when I said closest, that's not quite right. What I meant was the lowest value. And same thing up here, this would continue, so obviously you wouldn't want to use that when you're all the way up here. And for this example, this 1, 2, 3, etc., that's your number of stages that is required to get your distillate composition and feed composition, etc., that you state. So now that I've actually shown that, we're going to set the Y equilibrium as the minimum of Y rec and Y strip so that it can choose which one of those is the minimum. And we also want to append again the X equilibrium and Y equilibrium values, because they get updated throughout. Then outside of this for loop, our XY steps, this is kind of a list or array, I guess I should say array of these steps. So we're going to say numpy dot array XY steps. And then XB and XY steps, basically what this is going to do is print the target bottoms value and the actual value that we have. Now it should hopefully be safe to start the plotting. So as always, fig equals make subplots. We want to add a scatter. First we're going to do that rectifying line where X is equal to the distillate, etc., Y value, and then I'm also going to set a mode, and I'm also going to name this so that it's easy to see on our graph. And then we're also going to add a scatter for the stripper, for the stripping operating line. Some of this is right, so I'm going to take that. Basically, I just took that because it had the mode and name that I wanted, but this is not correct. Here, VB plus XB divided by VB plus 1. Then I need the Y values. And that should be good there. I'm also going to add the Q line, which we talked about in the previous video, but that is basically the how much liquid is present in the feed, or how much of the feed is a liquid. And that can contain both of the components in it. so since I'm not entirely sure all of this is typed in correctly, I'm going to go ahead and run it and see what it does. Okay, so from what I can see, the rectifying and stripping operating lines look good, kind of like this here, except the Q line does not look correct at all. So let me take a second look at what I did for the X and Y values. Okay, I completely mixed up this with the next step, but this should be similar to the X and be the Y underscore RS, which was the intersection between the rectifying and stripping lines until the feed, and I'm going to run that and see if it got fixed. So it looks much better. Now we want to do our steps, and it looks like Colab knows exactly what I wanted to do. So we're doing our steps from the beginning. It just named this incorrectly. This is not the equilibrium line. This is our stages. But we do need the equilibrium line, or I should say equilibrium curve. So fig.add scatter once again. X is equal to the X equilibrium, Y is equal to the Y EQ, same mode, and this name is the equilibrium curve. And we also want to do a 45-degree reference line. So we're going to do add scatter. X is equal to 0, 1, and Y is equal to 0, 1. Mode is equal to lines. And the name is going to be Y is equal to X. I also want to update the layout so that I can set my width and height, and make sure that my legend shows. So that should be true. And fig.show, and let's run this and see what happens. Positional argument follows keyword argument. Oh, this is supposed to be Y equals YEQ, not underscore. All right, so what we got here, first glance, you see this and you're like, that doesn't look right, because these aren't underneath our curve. They aren't underneath the equilibrium curve. And that is because of what we did with this, with our chosen values. So first I want to show what a slightly higher reflux ratio does. As you can see, immediately lowers those lines. So that's why I was saying in part A, when you have a really, really low, or if you had no reflux ratio at all, so if I set this to be really small, this wouldn't work at all, whatsoever. And then if I had that, just to make sure I cover all the bases, if I had 1000 as my reflux ratio, it's so high that it is perfectly, the stripping line and rectifying lines are actually perfectly against this Y equals X curve. And so this would be, in an ideal world, our ideal number of stages. And then 2, 1.5, and 1. So if we had 2, I think I already showed 2, so I'll show 1.5. Still above. And 1 is going to be even further up. So I think a good reflux ratio for now is 5. Yeah, so that looks like it's okay. Obviously, if you have a really high reflux ratio, you're not going to have as many stages. However, your whole process is going to take quite a bit longer to work, basically. And the next thing is if we alter this relative volatility. So for reference, this is what it looks like with a relative volatility of 2. And when I change that to 5, this equilibrium curve becomes much taller. And there's much less stages, which are these steps right here. And that is because a high relative volatility means they have much more different relative volatilities, which means that one is much more easier to vaporize than the other. And that makes the whole process a lot quicker and more simple. So with that higher relative volatility, I might be able to have a reflux ratio of 1, and it might not break it. So as you can see, depending on obviously a lot of other factors, but if you're just looking at the relative volatility and the reflux ratio, if you have a higher relative volatility, you can have a lower reflux ratio. So I think that 2 would be pretty good. And so I showed all of those, but I'm going to do an alpha of 3 and see just what that looks like. And yeah, there we go. As you can see, we would have 1, 2, 3, 4, 5, 6, 7, 8 stages. Distillate composition is this X value here. So as you can see, or I guess I shouldn't say composition, but the purity. Same thing. The composition or purity is 0.908, and this was our recovery. So that all looks pretty good. And to show a different Q line, if I cut that in half, it changes the angle. In the previous video, I talked about kind of what the different values of Q mean, but I'll keep it there. And so I think we covered all the bases here. We automated the generation of our McCabe Thiele diagram, depending on what your chosen relative volatility as well as reflux ratios are. And I kind of explained what happens when those change. A higher relative volatility means it's easier to separate and it'll need less stages. A higher reflux ratio basically means you're approaching that 45-degree line and you will have your minimum number of stages. However, it might take longer for the process to go through because remember that reflux ratio is comparing what you're refluxing back into the column versus the distillate you're taking out. So if you're not taking out a lot of distillate very quickly, this could take a much longer time. And so the last thing we want to talk about in this part is if we have an existing operating column, which is typically what you would see on the job, you're not going to change how a column is. Once it's built, that's generally how it is unless there's something wrong with it. So if we have an existing operating column with a fixed number of stages that we can't change, what happens when the reflux ratio is reduced? So what happens when you reduce it is your separation will not occur as well as it would otherwise. And I'm going to try to explain that on my end screen as well. But essentially, as the reflux ratio decreases, less liquid is returned back to the top of the column and more distillate is drawn off, as I had already kind of said. the mass transfer across the stages is reduced because you're taking off a lot of that volatile component, not allowing that transfer to occur as efficiently. And since the columns are fixed and you can't really change that, you would see a decrease in your purity, which can obviously be a big issue. So to reflect this on a McCabe Thiele diagram, you would not be able to fix your distillate and bottoms composition or purity that you want. You would need to use more of a guess and check method. So you would basically guess a distillate composition that you want to have. You would calculate the resulting bottoms composition and plot as you normally would, and you need to adjust the guesses until those theoretical stages match the physical stages. There might be another way to kind of do this, but from what I understand, that's a good way to do it. And that is all I have for you guys, so thank you for watching. Stay tuned for part C, in which we will be doing a lot more deriving, which is always fun. And then part D, we're going to talk about what we can't, why we can't always use the McCabe Thiele and our alternative options. So thank you for watching, and I'll see you in the next video.